Okay. Hello, everyone. It's great to be here. Thanks for the introduction. I'm Kai. I'm from QuTech in the Netherlands. And today, I'm going to talk to you about this diamond that you see here. Well, this is a replica of a diamond, but actually, it's the replica of a real diamond that we have in our lab. Is there a microphone? Yeah, perfect. So it's a replica of a real diamond that we have in the lab, just zoomed in to a really, really tiny volume of about 10 cubic nanometers. And what you see here is mostly those white balls. That's carbon-12. Most of the carbon in the diamond is carbon-12. However, about 1.1% of the carbon, those are those yellow balls, is carbon-13. And that has a spin. That's spin 1/2. And naturally, that forms a large coupled spin system in diamond that's coupled via dipolar interactions. So I said this is a real replica of the diamond in the lab, which means those yellow diamonds that you see here, we managed to pinpoint them with atomic precision. So what I want to talk to you about today is how can we actually observe those single spins in diamond? How can we control them? How can we engineer their interactions? And then also, how can we use them to study many-body physics? All right, let's start. How can we observe and control single carbon-13 spins in diamond? Well, we have to use a quantum sensor, and in particularly, we use a nitrogen vacancy sensor in diamond. That is also a lattice defect where one of the carbon atoms is substituted by a nitrogen atom, and next to it, there's a vacancy. And this traps kind of 2 electrons at the sides. So we have like a spin-1 system for an electron, and we can use that to sense the environment. So here you see the energy levels of that spin-1 system. We can read out optically the spin state, and we can control the spin state with microwave radiation. And the way it looks in the lab is that we have this slab of diamond that's glued on a PCB. It goes into a cryostat at 4 Kelvin. And on top of that diamond, we need to do some kind of nanofabrication. So in order to get lots of light from that NV center, when we read it out optically, we mill a lens into the diamond. And also to bring that microwave radiation close, we kind of pattern a golden strip line on top of the diamond. And here you can see a fluorescence image of within one of those solid immersion lenses, there's one NV center. And this is what we're going to use to sense the environment. But first, let me show you some numbers about that central electron spin. So optically, we can initialize and read it out with high fidelity. And also, it has quite good spin coherence. So at 4 Kelvin in the cryostat, the relaxation time of that spin, if we prepare it in one of the spin states, is of about 1 hour. And then the coherence time under dynamical decoupling is up to 1 second. But 1 second means we need to do about 20,000 of those dynamical decoupling pulses. So that means 2 things. We can do those pulses very, very well. We have very good control of the NV center. And when we do that, also we have long coherence times. But how do we use now the central spin to sense the surrounding spin 13 carbon spins? For that, let us look a little bit at the electron-carbon Hamiltonian. So what's the interaction between the central spin and the surrounding spins? And as I said, the central spin is a spin-1 system. So it can be in the m is equals 0 state, and it can also be in the m is equals -1 state. And if it is in the m is equals 0 state, you can basically disregard it, and all the carbon spins, they will just precess with the same frequency around the magnetic field that we apply along the z-axis. However, now if we turn on that central spin to the m is equals -1 state, it produces kind of a local field. And now it depends where, with respect to that central spin, that carbon spin is, to get a different frequency shift. And also there's a slight tilt actually in the axis. So there are kind of those 2 scenarios. If we shine in an RF field, in the left scenario, we can drive all the spins at the same time because they all have the same precession frequency. And at the right scenario, we can kind of target individual spins and make them rotate. So you can see that those are already kind of ingredients also to make an entangling gate, a C0 gate, like between the control, that's the electron, and a carbon atom. However, one of the problems is that in order to keep the coherence of that electron spin during like an RF pulse, we do need to decouple it most of the time, if it's not in an eigenstate, if it's like in a superposition. So how do we protect the electron from decoherence during the gate? And how do we make this entangling gate now? Well, we have to use this dynamical decoupling. So we flip the electron spin periodically. So now you see those purple pulses are all pulses on the electron, pi pulses. So for example, we would start in m is equals 0, then m is equals -1, m is equals 0. And we apply those yellow RF blocks at the resonance frequency for when the electron is in the -1 state. So then actually only every second of those blocks will be resonant, and the other one will just, to first order, not do much. And now it doesn't really depend anymore on which state the electron was at the beginning. We will always kind of rotate that carbon spin. It can even be in a superposition. The trick now to make an entangling gate is to adjust these phases in such a way that if the electron starts in the 0 state, we do a -x rotation, and if the electron starts in the -1 state, we do a +x rotation. This is maybe a little bit quick, but this way we can do a controlled rotation gate. So this means now we have kind of complete control over this 2-qubit system, the electron and the carbon spin, and we can use that to make gates. We can use that, for example, also to initialize our carbon spins and to read them out. And the initialization, for example, works like this, where imagine that carbon is in a mixed state in the beginning, and that electron is in a determined state. Well, we do an entangling gate, and then we read out the electron, and then by post-selecting on the measurement, we can project that carbon spin on a certain axis. And the readout actually works in exactly the same way, just here we don't post-select. And we can also do kind of these parity readouts by concatenating these entangling gates. So this is cool, and this means that we have kind of universal control with the electron spin over a register of those carbon spins. And this has been shown in the past in our group, where we've made this a 10-qubit solid-state register, and we've also used it to encode like a logical qubit in that register. And gate fidelities now of like the central spin to maybe the 3-4 strongest coupled carbons are about 99.5%. So actually pretty good. The long-term view at QuTech is that we want to combine these quantum processors with long-distance entanglement. So this kind of goes back to experiments that have been done in the group of Ronald Hansen, where, for example, in 2015, they've done this loophole-free Bell test and entangled over 1.7 kilometers 2 of those NV center spins. And recently also they've made a 3-node network that also had one of those carbon spins in one of those nodes. And you can use that also to make some distributed quantum computing. But that's not what I want to talk about today. Today I want to talk about that cluster of carbon spins, spin 1/2s. How do we find out the couplings, and can we use this to do some interesting physics? So we have this NV center, that's our quantum sensors. How do we actually find out couplings between the carbon spins? For example, between those two carbon spins. We have to look into NMR literature a little bit, and there is something that's called spin echo double resonance, and it works as follows. So we have here the electron, we have spin 1 and spin 2, and we kind of initialize all of those spins, and then on spin 1, we do a Hahn echo sequence, where this is basically a Ramsey, but we have this pi pulse in the middle, and what this pi pulse does, it decouples that spin 1 from the rest of its environment. So if we read out with the electron, that spin 1, we basically just get a flat line. Now we can put at the same time on that spin 2 another pi pulse, and that couples back in that second pi pulse. So that first pi pulse on the first spin decouples from all the environment, and that second pi pulse couples in now, so that we only see the coupling between spin 1 and spin 2, and when we then read out, we see an oscillation, which is exactly the coupling between those two spins. So then there was a project from one of our PhD students, Guido, who asked, how do we use this now to find 50 spins in the environment of the NV center? And it's actually really hard to read out the spins the further you go away from the NV center, because they become essentially indistinguishable. And what we came up with is that you can use kind of chains that go through the diamond and to read out the spins that are far away, because each spin then again sees kind of its local environment the strongest, and by doing some correlated measurements with chains, you can still access spins that are far away. So he used this to characterize kind of a 50-spin cluster. So this is 50 measured frequencies, 250 measured interactions, and this was enough to construct kind of a graph here of the whole spin cluster. So that's great. As a recap, we know the positions and couplings of 40 to 50 spins around the NV center in diamond. We can individually initialize them, read them out, control them. There's something that's a little bit missing is, can we also collectively polarize them? Because otherwise, we would really have to go one by one and initialize them all. That might take some time. But there are some ways to collectively also polarize the spin mirth. And that is done by a sequence that's called pulse pull. So these are just pulses on the electron spin, that central spin. And what it does is it engineers some flip-flop Hamiltonian between that central spin and the surrounding spins. And then periodically, you can reset that central spin. And if you repeat that many, many times, you will spread the diffuse kind of the polarization from that central spin and polarize kind of a bubble around your central spin. And this works reasonably. We've here, at least for 42 spins, kind of measured how it polarizes. And here also you see it's coupled with the readout fidelity, so it's all uncorrected data. But we can kind of, with good fidelity, get signal from about 42 spins. So you can see that very good fidelity you can only get from the closest spins, but still we can use a 40-spin cluster to do some maybe interesting physics. So we have this open system of carbon-12 spins around the NV center, and we know the couplings about 50 spins. We can individually address 40 spins and also initialize this bubble with kind of a good fidelity. Now I want to talk about how do these spins interact. Can we engineer this interaction, and can we use that to do some many-body physics studies? All right, so now I want to show you a little bit the Hamiltonian between those carbon spins. If we are in the ms equals 0 state, and in the ms equals minus state, already I showed you before, there are slight differences. So there are these two different regimes in which we can be. And one of them is where we have that hyperfine interaction between the central spin and the carbon spins. And this kind of gives us some disorder in some IZ term that's on the order of, so that distribution is on the order of tens of kilohertz for the closed spins. And in this case, we have some local microwave control. And if we have that central spin in ms equals 0, we have that global microwave control. And now there are these dipolar interactions. So in the first case, we have kind of a full dipolar Hamiltonian where we have the IZ-IZ coupling, but also those flip-flop interactions. In that second case now, we are in the end just left with an easing type of Hamiltonian because those flip-flops are resonant processes and they are kind of suppressed by that disorder that you have on each side. Of course, that disorder from that central spin falls off with 1 over r cubed. So at very large distances, the spins can still flip-flop. But close to that central spin, you kind of have a frozen core, and you have kind of an easing type Hamiltonian. Let me show these examples in some experiments where, for example, you initialize now all spins up with this pulse pull sequence that I've shown you. Then one spin with an individual pulse, we flip it down. And then we let the system evolve freely. And we can read out the subsystem. I'm only showing you now 4 spins. And you can see that 2 of those spins now start to flip-flop. And also the green spins and the blue spins kind of start to approach each other. in this kind of subsystem, the magnetization is roughly conserved over these time scales, even though you see it's growing a little bit. But that is kind of the Hamiltonian, the full dipolar Hamiltonian that we have when the electron spin can be disregarded. Now, if we turn on this local disorder, you can see, I've just plotted this for one spin, that you freeze the interaction. No more flip-flops. Now that spin 17 here, instead of flip-flopping, it kind of just stays in its down state. So if we, however, just look at m is equal to 0, we have this dipolar Hamiltonian. You can see that we have this short time relaxation, and then over a long time, the polarization will actually diffuse outwards. So we cannot do experiments forever. We have this bubble that we polarize, and over time, because the bath is still unpolarized, that polarization will kind of diffuse out. And the time scales of this is roughly 1 to 2 seconds here. So that red line kind of signifies that in short time scales, if we look kind of close to the central spin, that polarization is kind of conserved, but then it will flow out of that bubble. It's over some time. Contrary, if we have it in the m is equals -1 case, actually even after 10 seconds, the polarization is still there. And we've done these experiments also in the order of like 10 minutes for one spin, and that T1 time is really, really long. It's really, if it's in the frozen core, it does not flip-flop. Okay, now I've shown you a little bit those Hamiltonians, and I want to ask the question also, can we engineer this interaction? For example, we have this flip-flop interaction between those two spins. Can we stop that flip-flopping by only applying global pulses, like pulses on all of the carbon spins? So we're not echoing out the single carbon, but we only apply pulses on all the carbons at the same time. And yes, this is possible with techniques from NMR, basically. For example, one can apply this Wahua sequence here, which just consists of a sequence of global pi/2 pulses that we do on all of the carbon spins. And if you do this, to first order, kind of the interaction Hamiltonian will average out to 0. So if we repeat this sequence many times, we can freeze, for example, this initial state. Now this is over 60 milliseconds, where before kind of a period was like 20 milliseconds. So we've frozen it out for like 3 oscillations, and then afterwards we let it go, and it still kind of starts to flip-flop. Maybe this is a little bit a boring example because it's a kind of, you start with a product state. We can also first let it flip-flop into like an entangled state, then try to freeze that entangled state, and then let it go again, and it still starts to kind of flip-flop. There's something that we can also do that we're recently trying out, is that if you leave out certain timings in that sequence, you can actually reverse the time evolution. So here, for example, on the bottom graph, we let it first freely evolve, kind of freeze the interaction for a little bit, and then we turn back time with this global sequence, and you can see that spin 17 goes back to its initial state, and also C11. So we have, and we're exploring this at the moment a little bit, we have the capability, because of the structure of our kind of dipolar Hamiltonian, to engineer also a time reversal in our system. And this could be, for example, interesting to measure something like OTOC, the out-of-time correlation. And this can give us some information about the spreading of some weak or local or global perturbation. For example, you let your system evolve for a bit, then you make some small perturbation, and then you have to evolve it backwards. And this can tell you something about how fast that global or local perturbation kind of spreads in the system. That can tell you something about how entangled it is. All right. So now I want to take you through an example of kind of a quantum simulation project that was done in the past in our group, where we isolated a 1D chain now in the system of these 9 spins. And we realized many-body localized discrete time crystal on our system. So here you can see in yellow those 9 spins along the cluster, and the coupling with kind of side distance falls off with our normal power law, and kind of essentially that coupling has some disorder because the spins are kind of just randomly distributed over our diamond. And that this order is essential for us to have kind of these localization phenomena. But first, I want to tell you again how we isolate kind of the spin chain. And the way this works is that now we kind of work in this Ising type Hamiltonian. And what we can do is we do multi-tone pulses. So here, for example, on 3 qubits, and we flip those periodically. But the bath is kind of always in the same state. And when you do that, you will average out the effect from the bath, and you will still conserve the interaction within that chain. And we've shown this, and it works actually reasonably well, that even if you initialize, you take those 4 spins, you initialize them all in X, and then you do these echo sequence on those 4 spins, you can preserve kind of the interactions within the chain and decouple them from its environment. So we have this 9-spin chain now, and we want to make this time crystal, but let me give you first a little bit of a background on what a time crystal is. So a time crystal breaks discrete time translation. What that means is just that we have a Hamiltonian that's periodic in time, and we have some observable, like the magnetization, that's periodic with a different periodicity, for example, 2t, with a longer period. So this is period doubling effect. And important is also that there's some kind of rigidity to that phase. So even under perturbations of the system, that phase remains stable. For example, if we don't do perfect pi pulses here, but we do over-rotations, usually you would say those over-rotations will add up, and you get some kind of a beating or oscillation. But in this case, if you're in the time crystalline phase, those don't add up. So you do imperfect pulses, but the system always comes back to its initial state. And that is kind of interesting because you can also say it breaks ergodicity. Even a high energy state kind of does not thermalize, and in theory would live on forever. So we wanted to probe this phase diagram, and here on the x-axis you have the pulse imperfection. And what we can also sweep is the interaction time. So we can't change the strength of our interaction, but we can let the system interact for longer. And here you see that, okay, you want to be off that pi. You want to introduce some pulse imperfections and see that if you increase the interactions, you get into that phase where those pulse imperfections are kind of corrected for, or that initial state does not decay. And if you look at the experiment, and this is kind of an average correlation over those 9 spins, you see that for small interaction time, that signal decays very fast. But if you are in this many-body localized phase, the initial state is preserved over like hundreds of cycles. So that's quite cool, but our system can also do more than just average correlation because we have single-site observables. So we can initialize different initial states and really look also not only, for example, what like a all-spin up state would be, but also kind of a nail state would have for a signal. And you can see even a nail state kind of lives on for hundreds of cycles. In fact, it didn't matter which kind of initial state you prepare, what kind of energy density that initial state had, that decay always had the same kind of time scale. And that is really a hallmark signature that we have localization in the system. And yeah, what we want to do now a little bit is we have done these experiments in 1D, in the 9-spin chain. And there we are pretty sure that we have this strong localization. We can also look in 3 dimensions that we don't necessarily expect that we have this localization as strong because just it's possible to find more partners to be resonant with and thermalize with. But still, with microscopic control and observables, we might be able to pinpoint those thermalization processes and look really what happens at to different spins. So just as an example, for example, we've done now these experiments, and we're analyzing data of now these 40 spins that we have. And if you look at initial time traces, And here you see kind of the odd and the even pulses. For this particular spin, it still lives on after like 200 cycles, which is about 2 seconds, by the way, for us. But another spin actually decays very, very quickly. So maybe this spin managed to thermalize very quickly because it found some kind of partner in the system. And we're trying to go into this direction now of looking at thermalization with kind of microscopic observables in the system. Now,
about 1 minute.
Yeah, it's just 27 minutes.
Oh, sorry. Sorry, my mistake. Sorry.
So this was, in the past, this was kind of looked at in literature, but for kind of ensembles of NV centers where it's also in 3 dimensions, but we didn't have this local control. So we only had global observables, but then, for example, something like a nil state or so, you would get no signal. So we think this can be quite interesting to study these thermalization processes. Then in this state where we have the full dipolar Hamiltonian, we really don't expect any localization, and the spin diffusion should be limiting, we think. But actually, when we look at experiments, this is kind of now really combined, where we have those 40 spins, and we all put that like in one number. In the decay curve, we look at the average correlation over what time scale it kind of decays. You see that if we increase the interaction time, it kind of saturates relatively quickly, and it actually saturates much earlier than that T1 decay that we have for that spin diffusion. So here, we are still exploring this, but it seems like we are not actually limited by that spin diffusion, but we are already limited by something else. This kind of looks like dephasing, where it doesn't depend on the interaction time anymore, and it seems like we're just dephasing really quickly. But this is still to be explored. So as a summary, I've told you how we can observe and control single spins, single carbon-13 spins in diamond, by the use of this nitrogen vacancy center that is in its vicinity. We can use that nitrogen vacancy center to do gates, and we can map out also the couplings between those carbon spins. And we have some control over the Hamiltonian. We can engineer it from like a full dipolar Hamiltonian, where we have those flip-flops, to like an Ising type Hamiltonian. We are currently exploring those global pulse sequences to kind of freeze the interaction or revert the time evolution. And the physics that we can do is either we have this open system, or we kind of have a closed system where we do these multitone pulses, as I've shown you in this last example. This is, however, tricky to do for more than 10 spins. So right now, we are more interested in looking kind of at driving the whole spin path. With that, I want to conclude my talk. This is the team of Tim. So this is Tim Sarminio, my boss, and this is our team at QuTech. And you can see that Christina is over there. If you have any questions about the experiments, please feel free to approach her during the breaks. She will be sure to answer all of them, I think. Better than me, probably. Yeah, with that, I want to conclude my talk. But if you have any questions, please go ahead.
Thank you very much. Nice talk. So we have plenty of time for questions.
Thanks for the nice talk. I'm kind of curious for the first part where you talk about those reversal and the frozen core physics. Like, how well can you model the dynamics theoretically? Maybe I missed it. Like, can you extract all the measurements? Like, for example, in like the manual localization part, like there's, I presume, like a series curve compared with like the measurement data, but it would appear that in the first part there really isn't like a series curve, like when you show this. Like, is that correct, or?
Yeah, so this is data from like this week. I'm sorry. How well we can do this time reversal is a little bit limited. So we are a little bit. The way this average Hamiltonian works is kind of that you have to do kind of a Magnus expansion, and in principle, those time steps that you take must be shorter than the interaction timescale that you have in the system. And currently, this works well for most of the spins. However, if you have nearest neighbors in the spin lattice, those still have couplings of about 1,000 hertz. And this is just on the edge of the Rabi frequency with which we can drive all the spins. So we don't expect this to be perfect, but we haven't also, we need to still do the work to characterize this properly and see how this kind of affects also those spins.
Okay, can I make just quick follow-up? Like, so should I think of the regime of the dynamics to be still efficiently simulable classically, or like, because you also talk about the for these spins like thermodynamics, I'm just curious, like.
Yeah, I think it's a bit difficult for us because, of course, now in this case of those when we really want to talk to those 40 spins, it's also an open system, so it's not only 40 spins but many more. So it gets a little bit difficult to simulate for us. We think if you have a closed system of 10 spins, okay, we can still simulate it, but then for those large systems, we don't really know how to do the theory for that, I think.
So for instance, if you work with these closed systems with 10 spins, I guess it's already there challenging because it gets quite dense in frequency space. So how do you avoid a lot of crosstalk between all those? Because I guess if you do fast pulses, then you easily can talk to multiple spins and just instead of correct?
Yeah, you really you're limited to the spins that are kind of close to that central spin, and which are distinct in frequency. And those are really distinct from, those have the coupling to the central spin is still on the order of 100 kilohertz or so, which for us is still enough for basically to address them separately. But, and we made kind of tried these measurements where we saw how well can we actually decouple those spins, and this works actually quite well over long time scales. However, to do more than, so this time, I must say that this time crystal project was a little bit lucky also, because those pulses in the end also needed to be imperfect, where you wanted those pulses to have errors. It's really hard to calibrate a 9-tone pulse, because it's like a multi-dimensional optimization problem. You tune up one amplitude, but you get like stark shifts on other transitions, and it's a little bit difficult to make this properly. But here, the fun part was that it was necessary to have those bad pulses, and it's still in order, together with those many-body interactions, kind of it's corrected for, which is kind of the fun part, I'd say.
Thanks for the nice talk. I was just wondering, you said at the start that the 2-qubit fidelity was like 99.5%, if I remember right. What's the main limiter on that, and are there any ideas or prospects for improving that?
So this is a little bit ongoing work, and we have kind of a project that's working on characterizing those gate fidelities using gate set tomography on another spin cluster. Currently, actually, the main caveat seems to be really coming from dephasing. It can be either you do, so we do this these 2-qubit gates, and in the 2-qubit space, I guess both the electron could dephase, but also that carbon. And it's mostly the electron that seems to be limiting at the moment. But yeah, it's still to be explored. We want to explore this a little bit. You can kind of, for example, polarize the environment, and then that coherence should go up because it's mainly limited by other spins. Yeah, I think it's difficult for at the moment to go high. If you want many spins and fidelities that are much higher, it's going to be difficult. You can isotopically purify it a little bit, and that makes it maybe a little bit better in terms of coherences, but you're also less likely to have those spins around. Yeah.
Thanks. Other questions?
Can you tell us about the back action of your measurements on the spin? Have some back action, and how many cycles can you do without disturbing the?
Yeah, there's always, so if we read out with the electron, so we make those two qubit gates, there's always some back action, and there's like a phase, I guess, that we use. But I think your question was mainly like how many spins can we read out? And so the trick is that you always have to go via the central spin, right? So we can read out 40, but all have to be read out via the central spin. And currently we do this in blocks. So we kind of divide it up in 10 blocks, and for 5 to 10 spins, it depends on how far they are away. We kind of always do entangling gate, read out the electron, reset the electron, do an entangling gate, and that works kind of reasonable without the fidelities increasing too much. But it means also that there's quite a large overhead to these experiments, where we have to repeat now those experiments 10 times, because we do one block, repeat the experiment, do another block, repeat the experiment, do another block. So in terms of timescales for the experiments, it is quite detrimental that we cannot read out more than like 5 to 10 spins per experiment, basically, repetition. Yeah.
So I think we're out of time for questions for now, but let's thank Ike again.